As you settle in and let the edges of the day grow quiet, picture the Milky Way from within. We live in one of its spiral arms, far from the crowded center. There, behind pale curtains of dust and a knot of countless stars, something massive waits the hidden heart of our galaxy. It's called Sagittarius A, times a supermassive black hole with a mass of about 4 million suns. You can't see it with ordinary eyes. Dust steals the light we'd need, and the center is so crowded that everything blurs together. But with the right kind of sight, invisible colors like infrared and radio, the picture changes. Stars near the middle glide in tight, fast loops around an unseen point, and faint radio light outlines a delicate ring close to a boundary where even light cannot return. This is the paradox at the center of our home. The most extreme object in our sky is almost silent. It doesn't blaze like a quasar. It barely feeds, but its gravity shapes the motions of stars and gas quietly, setting the rhythm of the region around it. Before we go further, please like and subscribe. If calm, thoughtful journeys through space help you drift off, that simple tap helps us keep making them. For a long time, the center of the Milky Way was more guesswork than knowledge. Telescopes that worked like giant eyes could map nearby stars, but whenever they looked toward Sagittarius, the direction of the galactic core, they hit a wall of light and shadow. The bulge at the center is swollen and dense, with dust threaded through it like smoke. Visible light scatters and fades there, hiding whatever lies behind. So, astronomers changed the way they looked. Infrared light slips through dust more easily. Radio waves glide through almost untouched. With those new eyes, the wall thinned. The crowded core resolved into clusters and arcs. And deep inside, a compact radio source appeared at the very spot the stars seemed to orbit. Sagittarius A*. In the minutes ahead, we'll follow how that faint signal became a certainty, how an engineer chasing radio static first heard the galaxy's whisper, how a single star's 16-year loop weighed the darkness, and how a planet-sized camera traced a blurry ring, the black hole's shadow around the place where time runs steep. For now, let your breathing match the slow pace of that distant center. The galaxy's heart isn't loud or hurried. It's patient. And even from here, far out in the spiral, we can feel the quiet pull of what's hiding in the Milky Way's heart. To understand what hides in the middle, it helps to start with what hides the middle. Our galaxy's center is one of the most crowded neighborhoods in the sky, a swollen bulge where stars gather by the hundreds of billions. Threaded through that crowd is dust. Tiny grains of carbon and silicate and ice, leftovers from older stars, seeds for new ones. Dust is gentle to look at, but stern with light. It scatters and absorbs the same visible colors our eyes rely on, turning bright things dim and distant things invisible. From our position out in the spiral arm, when early astronomers pointed their optical telescopes toward the constellation Sagittarius, they met a wall, lanes of darkness crossing rivers of starlight. The near stars were clear, the far ones vanished. It looked less like a heart and more like a riddle. Optical telescopes are, at their core, giant eyes perfect for colors we can see, but not for a center wrapped in haze. Looking that way, the Milky Way's middle blurred into confusion, and for a long time people drew maps that made sense of the outer galaxy while leaving the core as a guess. Some even thought the sun might sit near the center because the hidden side looked so much like the side we could see. What changed was not the sky, but our approach. Light comes in many flavors, and not all are stopped by dust. Infrared light, longer in wavelength, slips through more easily, like a low note passing through a wall. Radio waves travel farther still, barely bothered by the fog. When astronomers built instruments to see and hear in those bands, the curtain thinned. From dry mountain tops, where the air is steady, new infrared cameras began to pick out stars in the core that were invisible before. Clusters appeared where darkness had been. Gas clouds glowed with gentle heat. The center, once a smear, began to resolve into a place with shape. Even so, Earth's atmosphere keeps much of the infrared for itself, absorbing some of the very colors we need. So the quest climbed higher on aircraft and balloons, and then floated free of the air entirely. In orbit, space telescopes could collect the faint warmth of dust and the shine of crowded stars without the atmosphere's shimmer. Maps that were once blank filled in with quiet detail. Switch to radio, and the picture changes again. The bulge hums. Electrons spiral along magnetic fields and broadcast their presence. Molecules in cold clouds emit at precise, telltale frequencies. In this new view, astronomers found not just a crowd, but a pattern arcs and filaments threading a complicated core. And right at the dynamical center, where the motions of stars seemed to converge, a compact radio source stood out. It was small as seen from Earth, steady, and exactly where a heart would be. We call it Sagittarius A**. Seeing that point was one thing. Understanding it was another. The center is busy. Stars overlap in our line of sight. Gas blurs the view. Magnetic fields twist the light in subtle ways. A single image could never settle the question. The only way forward was patience. Watch how the center moves. So teams began to track individual stars tucked near the core, measuring their positions carefully and returning season after season. Each star became a marker, a way to read gravity's handwriting across the sky. Over years, then decades, the confusion softened into clarity. The orbits traced ellipses that all pointed to the same hidden mass. This is how a wall became a window, not by forcing the eye, but by changing the light, and by letting time do its quiet work. The heart wasn't loud. It didn't announce itself. We learned to find it by noticing how everything else moved around it. In a moment, we'll meet the first person who heard the center before we ever saw it. A radio engineer chasing static who realized the noise kept time with the stars, not the Sunday. His discovery opened the long, calm road that led us into the Milky Way's heart. In the early 1930 seconds, a young engineer named Carl Jansky was asked to track down a stubborn kind of radio static that sometimes leaked into long-distance calls. He built a curious, rotating antenna nicknamed the merry-go-round and listened for months. Thunderstorms spoke loudly. Distant lightning murmured. But there was a third whisper, gentle and regular, that returned a little earlier each day, about 4 minutes early, keeping time not with the sun, but with the stars. Jansky traced that whisper to Sagittarius, toward the crowded center of the Milky Way. He wasn't trying to do astronomy, but he had opened a new door. The sky was bright in radio. We simply hadn't been listening. A few years later, another radio enthusiast, Grote Reber, read Jansky's report and continued the work. In his backyard, he built a metal dish about 9 meters across and began to map the radio sky, one patient sweep at a time. Where optical maps showed darkness and dust, Reber's radio map showed structure. A broad band of emission traced the plane of the galaxy, and the region toward Sagittarius glowed brighter than most. That was the beginning of radio astronomy as a craft. Over the next decades, single dishes grew larger. Then came arrays, many antennas linked together to sharpen vision and pick out finer detail. The Milky Way's center, once a smear, resolved into a complex place. Filaments and arcs, knots and curves, each telling a part of the story. At the very heart of that tangle, astronomers found a compact radio source. They called the surrounding region Sagittarius A, the first strong radio complex in that patch of sky. Look closer still, and a particularly tight, intense point stands out at the exact dynamical center, the place other objects seem to orbit. In the early 1970 seconds, careful observations isolated that pinpoint. It was given a small, telling mark, an asterisk, Sagittarius A asterisk. The asterisk had a quiet poetry to it. In atomic physics, it can mark an excited state. Here, it signaled something concentrated and unusual, more compact and energetic than the rest of Sagittarius A. The name stayed, and so did the mystery. Even then, Skr A times was just a dot in the noise. It did not announce itself with jets or nightly flares. It did not show a surface. It only persisted small, steady, central. Many ideas were tested against it. A cluster of dim stars, a dense ball of stellar remnants, a cloud of exotic matter. Each faced the same problem. Matching the observations required an object far too compact to be ordinary. Pictures hinted at an answer, but pictures alone were never going to be enough. To know what the dot was, astronomers would have to weigh it. There isn't a scale big enough for the heart of a galaxy, so they chose a gentler method. Watch the way stars move around it, and let gravity reveal itself through their paths. Dust still hid the center from optical telescopes, so the work shifted to infrared, where the fog thins. Earth's atmosphere shimmers, so images needed help from techniques that calm the twinkle and make stars sharp. Season after season, the same points of light were measured again and again until their motion drew clear shapes on the sky. A handful of specific stars, bright enough and close enough to trace, were given simple names, S stars, and placed under careful watch. One of them, S2, would reveal almost everything. A long, elegant orbit through the crowded core, moving so fast near closest approach that only a single, compact mass could explain its path. From that motion, the center of the Milky Way weighs in at roughly 4 million suns, packed into a space no cluster of normal objects could survive. Quietly, the evidence points to a single, simple conclusion. On high plateaus where the air is thin and dry, telescopes were fitted with sensitive infrared cameras. But starlight still has to travel through a restless sky. Pockets of warm and cool air bend it in shifting ways, making points swell and quiver. To calm that shimmer, engineers developed a graceful solution. Adaptive optics. A sensor measures how a reference point twinkles. A thin, flexible mirror responds hundreds of times each second, changing shape by amounts smaller than a human hair. One moment, the mirror curves a little more here, the next a little less. There, always, nudging the light back into focus. Some observatories make their own reference by sending a narrow laser upward to create an artificial point in the high atmosphere. The mirror listens to that point and corrects the whole image in real time. What was fuzzy becomes crisp. Stars shrink from blurs to tight, steady dots. With that clarity, the central field, once a confusion of overlapping glows, turns into a map. Individual stars near Sagittarius A times can be chosen, labeled, and followed. Night after night, season after season, their positions are measured with quiet care. Each new measurement is a small footstep. Together, they trace a path. Space offers a calmer vantage. Above the air, infrared light isn't absorbed or blurred. Spaceborne observatories collect the faint warmth of dust and the glow of crowded star fields without atmospheric interruption. Ground and orbit complement one another. The ground offers giant mirrors and quick upgrades. Space offers stillness and dark. Back on Earth, adaptive optics keeps writing its gentle signatures. A star that looked immovable at first begins to drift a fraction of an arcsecond. Another loops slightly closer to the center. The lines these motions draw are small, but they are consistent. Data taken years apart agree with data taken last night. Even in a busy, glowing core, a pattern emerges. The work is quiet and patient. A typical observing run begins at twilight, when domes open and the last warm air slips away. Instruments cool to the temperatures they need. The laser guide star climbs until the sensor is satisfied. Then the camera gathers a stack of brief exposures, rather than a single long stare. Short frames catch sharp moments. Later, the best are aligned and combined. The result is steady detail in a place that once refused to hold still. From those steady images come numbers the exact centers of starlight, measured over and over. Each measurement has an uncertainty, and each uncertainty is recorded. The values are not dramatic on their own, but strung together, they become a curve. The curve becomes an orbit. Infrared astronomy also reveals what hides between the stars. Warm dust outlines lanes and arcs. Faint knots of gas drift near the core, some tugged inward, some held back by the churn of magnetic fields. Occasionally, a small flare brightens in these wavelengths, rising and fading in less than an hour. Even the quiet center has weather. As more seasons pass, the map near Skr A times fills with tracks. Some stars move slowly, their loops wide. A few hurry along tighter paths. The closer a star travels to the invisible center, the faster it must go to remain on course. That change in speed is a clue to the mass that holds it. What infrared and adaptive optics make possible is simple in spirit and delicate in practice. Watch the sky draw its own geometry. Let gravity write in starlight. In a region where dust once hid everything important, the combination of longer wavelengths, stable images, and patient timing turns a rumor into a result. Among the many points of light near the core, one star in particular proves especially helpful. Its path is long and elegant, and at its closest sweep it moves with a speed that leaves very little room for ordinary explanations. The mass it answers to is heavy, compact, and dark. About 4 million suns gathered into a space too small for any cluster of normal objects to endure. The conclusion arrives without hurry. Infrared light, a steady mirror, and time make it difficult to argue with the shape of a curve. Where once there was only a compact radio dot, there is now a weighed, tested heart at the center of the Milky Way. From our distance, about 26,000 light-years, S2 looks like a modest point. It brightens and dims with the seasons of observation, but otherwise asks for no attention. The meaning lies in its motion. Year after year, it draws a long, graceful ellipse around a ellipse, place that is almost empty of light. Each time it comes nearest that center its pericenter, it moves at a speed that is hard to fit inside the mind. Thousands of kilometers each second. Fast enough to cross the Earth-to-Moon distance in a breath. The curve is not guessed. It is measured. With infrared cameras and mirrors that hold the image steady, S2's position is recorded again and again. Each dot on a plot is small on its own, yet together they form a line that deepens with time. The ellipse closes. A period emerges about 16 years for one full loop. There is a quiet satisfaction in this kind of knowledge. No drama, just the same sky visited patiently until it starts to speak. The language is geometry, a set of positions that only make sense if an enormous mass is tucked into a space smaller than our solar system. If that mass were spread out, if it were a cluster of faint stars or a ball of old remnants, the orbit would wobble in ways it does not. The star would tug on neighbors and be tugged in return. The center would blur. Instead, S2's path points to a weight that is compact and central, the way a stone anchors a sling. As S2 dives through pericenter, another subtle sign appears in its light. The spectrum leans to the red, not because dust reddens it, but because the star's photons must climb out of a steep gravitational well. They give up a touch of energy to escape. This gravitational redshift is a small effect, predicted by general relativity, and difficult to see without careful instruments. Here, it shows up where it should, when it should, with the size it should. There is also a slow twist to the orbit itself. If gravity behaved exactly as Newton imagined, S2 would trace the same ellipse forever. But the space around a very compact mass is not a flat stage. It is curved. Each time S2 swings by the center, the ellipse turns a little, advancing its orientation like the hand of a clock that moves barely a fraction at each tick. This is Schwarzschild precession, a gentle, cumulative nod to Einstein's picture of gravity. Taken together, the speed at pericenter, the redshift of the light, the precession of the ellipse, the signs agree. The object at the focus weighs in at roughly 4 million suns and is packed into a volume so small that ordinary matter cannot support itself there. The simplest, most durable explanation is a supermassive black hole. It is tempting to rush past the stillness of this result, but there is something restful in the way the conclusion arrives. No single image proves it. No one night compels belief. The truth gathers as a tide does, grain by grain, line by line, until it is simply there. S2 is the cleanest voice, but it is not alone. Other stars fainter, sometimes closer, add their small agreements. Each orbit is a quiet vote that points to the same invisible mass. The numbers can feel sharp, so let them soften into images. Imagine a city seen from very high above, blurred by distance and haze. You cannot make out the streets, but if you trace the headlights of a few cars long enough, the pattern underneath appears. There are curves, circles, a center where traffic swirls. S2 is a bright headlight in the galactic night. Its path reveals the roundabout we could not otherwise see. When S2 is far from the center, it lingers, moving slowly as if unwilling to leave. As it drops inward, it quickens, and time seems to compress. Near pericenter, the star is a pale spark racing along the inner edge of a bowl. Then the speed eases again as it climbs back out. This change in pace is not just pretty, it is necessary. Only a tightly concentrated mass can hold a star to such a curve. Only a deep well can permit such a dash without tearing the star apart or flinging it away. There is a period after pericenter when observers breathe a little easier. The measurements around the closest approach are demanding. The angles are small. The star sits in a crowd. The atmosphere must be calm. The instruments must be exact. The corrections must be right. When the data from that passage fall into place and match the long curve, it confirms not just the theory, but the craft, the years of work that let tiny changes be trusted. General relativity can be described with heavy mathematics, but its sense can be held in a few thoughts. Mass tells spacetime how to curve. Curved spacetime tells mass how to move. Near a very compact object, paths that would be straight go a little round. Time that would run evenly slows a touch. Light that would keep its color shifts a little. S2 passes through that neighborhood and carries back the news in its motion and its light. Not every detail is settled. The exact spin of the black hole at the center, how fast it turns, and the tilt of that rotation remains under study. The closer a star orbits, the more future measurements may reveal. Some stars may yet be found on even tighter tracks, their pericenters, nearer the invisible edge where time runs steep. For now, S2 gives the clearest, calmest constraint. It sets the scale. Sometimes it helps to compare. The event horizon of the Milky Way's central black hole would fit well within the orbit of Mercury. The entire region that S2's motion requires, the place where nearly all that mass must live, is not much larger than the space spanned by our planets. 4 million suns, implied by the motion of a single star, held in a darkness you could cross in hours at the speed S2 reaches. The mind may reach for escape chambers. Could it be something else? A cluster of dark objects, perhaps black dwarfs or neutron stars packed somehow together. The orbits push against that idea. Such a cluster would scatter and heat itself, breaking apart over time. It would likely collapse to a black hole under its own gravity. Exotic solids, hypothetical particles woven into a ball struggle with the same compactness. The simplest shape that holds is the same. One theory points to a black hole. S2's work is not to be dramatic. It is to provide a foundation. On that foundation, other kinds of seeing can stand. A planet-sized radio camera can now look for the shadow where light bends and falls in. Polarization maps can trace magnetic fields as they funnel and restrain hot plasma near the edge. Flares can be timed and compared against the clock set by gravity. All of that is steadier because a star drew a faithful curve for 16 years and then kept going. It is easy to feel far from the center. Our sun circles the galaxy at a quiet distance, and the night here seems gentle compared to the swirl at the core. Yet there is a connection in the calm fact of an orbit. The same law that guides S2 guides us too. We move more slowly and at a safer remove, but we are held by the same shape of space-time. The galaxy turns, and we turn with it, as if drawn on silk. The star will complete another loop. After that, another. Others will be found closer in, or fainter but still useful. The pattern they make will grow denser, and the conclusions will tighten in their uncertainty. None of this hurries. The core has kept its pace for billions of years. We take our brief watch and add a line to the long record. If you listen to the feeling of the scene, there is a rhythm: approach, rush, release, drift. It is not unlike your own breath settling at the end of the day. Inhale, the star falls inward. Exhale, it rises away. Between those movements is a center that does not need to move at all to command the dance. The quiet proof stands. The Milky Way's heart is heavy and small. S2 has shown us how heavy and how small. And with that weight and compactness known, a new window opens. Light skimming the edge can now be read in context. A blurry ring can be sized against a prediction. Sudden flares can be timed against the clock. A 4 million solar mass object keeps. For now, let the thought settle. A single star, measured patiently, can reveal the architecture of a galaxy, not by shouting, not by spectacle, but by tracing a path with enough care that the shape beneath becomes undeniable. The curve is gentle. The conclusion is firm. The center holds. Once the mass at the center was weighed by the motion of stars, a quieter wish remained: to see the shape of light near the edge, where gravity bends paths into circles and lets some photons skim the brink before they fall. That wish required a new kind of eyesight, one that no single telescope could provide on its own. At the wavelengths where the glow close to the black hole is strongest, ordinary mirrors will not do. Instead, radio dishes receive gentle ripples that have traveled for tens of thousands of years. To resolve something as small as the shadow of Sagittarius A asterisk, you would need a dish as large as the Earth. Since building that is not possible, astronomers linked telescopes across the planet, so they act, in effect, like a single, world-sized instrument. The technique is called very long baseline interferometry. Each observatory listens at the same time, guided by clocks so steady they scarcely drift at all. Later, the recordings are brought together, and the faint wave patterns are combined into an image. This global array is the Event Horizon Telescope. In April 2017, it listened to the center of our galaxy. The recordings were vast, the atmosphere was variable, and the target itself was restless. Close to Sagittarius A*, hot plasma orbits in minutes. While the Earth turns and the array samples different spacings, the subject changes its brightness and shape. Imaging becomes less like taking a photograph and more like reconstructing a melody from instruments that never met, while the score keeps improvising. The solution is to look for features that persist, sizes and arrangements that remain when the quick fluctuations are averaged away. There were other challenges. Between us and the center lie clouds of ionized gas that scatter radio waves, smearing fine details. Corrections can be made, but some sharpness is inevitably traded for clarity. Weather matters too. A world-sized instrument only works when many of its pieces can observe together. If a storm closes one eye of the array, a piece of the virtual mirror goes missing. Even so, with careful planning and repeated campaigns, the data arrived with enough redundancy to trust. When the first images were formed and checked against many approaches, a simple shape appeared. A ring with one side brighter, enclosing a darker middle. The center is not the black hole itself, but its shadow, a silhouette cast by gravity on the light behind and around it. The bright crescent arises because material near the hole is moving quickly. Emission from the side approaching us is gently boosted by relativity. Light from the receding side is softened. The ring's size matches the prediction for a black hole of about 4 million solar masses at our distance. The picture is not sharp in the way a photograph of the moon is sharp. It does not need to be. What matters is that the scale agrees with gravity's forecast, and that the features persist under different ways of piecing the data together. The image is best understood as a measurement, a confirmation that the mass weighed by starlight also carves space-time to the right size at the edge of visibility. It helps to hold a small comparison in mind. On the sky, the dark center of Sagittarius A times appears about as large as a donut set gently on the moon. To separate something that size from this far away, the array must be steady across continents, and the timing must be exact to fractions of a microsecond. The data cannot simply be emailed. They are too large. Drives travel by hand to special centers, where patient algorithms take their turn. The process is slow by design, favoring certainty over speed. The result also explains an earlier curiosity: why the first black hole ever imaged was not our own, but the more distant one in the galaxy M87. That object is vastly heavier. Near its edge, matter takes days to circle. Over the span of a night, its face changes very little. Sagittarius A times is light by comparison. Its appearance shifts in minutes, and the same variability that makes it a lively laboratory also makes it a hard subject. In spite of that, the ring emerged, a quiet, repeating outline found by many independent reconstructions. Seeing the ring does not end the questions. It sets a stage on which gentler measurements can play. The thickness and brightness pattern of the glow say something about how matter moves and how magnetic fields are arranged near the horizon. Slight differences among reconstructions whisper about how scattering along the way has blurred the view. As more stations join the array and new wavelengths are added, the outline will sharpen. The ring may be traced in polarized light, revealing the directions of magnetic fields that guide the plasma. Shorter wavelengths will cut through some of the smearing, and longer campaigns may one day yield short movies instead of still frames, letting us watch features drift around the circle. For now, it is enough to notice how the measurement fits with a quieter evidence from the stars. The orbits say the mass is 4 million suns, packed tightly. The ring says gravity near that mass bends light at just the right scale. Two very different senses, one following the motion of bright points, the other combining the whispers of distant radio waves, arrive at the same place. The agreement is calming. It suggests that even in this extreme corner, the same rules hold that guide the rest of the sky. The image is also a reminder of the patience built into the craft. Arrays must be assembled, agreements made, weather watched, clocks kept. Observing windows are brief. Data must travel. Teams repeat work in parallel, compare quietly, and choose methods that agree. In the end, what remains is not a single masterpiece, but a modest ring whose strength lies in how many ways it can be recovered. Hold the picture lightly, a soft circle with a dim center, sized just as theory expects, brightened on one side by motion. It is the nearest look we have yet had at the place where the Milky Way's gravity is most intense. Around that outline, other stories can now be told: the timing of brief flares, the paths of small hot spots that may circle and fade, the subtle imprint of magnetic fields in the glow. The portrait does not hurry these stories. It simply gives them a frame in which they can be read. It may seem strange that the first black hole image released to the world was not our nearby neighbor but a distant giant in another galaxy. The reason is timing. Near a supermassive black hole, matter orbits on a schedule set by mass. The heavier the black hole, the longer each lap takes. 87 times is billions of solar masses. Features near its edge evolve over days. Across a single night, it looks almost steady. Sagittarius A times is lighter, by a factor of 1,000. Close to its horizon, plasma can circle in minutes. While the Earth turns and the array listens, the subject itself changes shape. That difference turns imaging into a delicate averaging game. A long exposure would blur the changing face into something formless. Instead, many short measurements are gathered and combined, seeking what persists. The ring's size remains. A crescent brightens more on one side. Those steady traits are kept. The flicker is allowed to wash through. Between us and the center of the Milky Way, another difficulty waits: scattering from ionized gas in the galactic plane. Radio waves wander a little as they pass through this uneven medium, the way light shimmers when it travels through warm air rising off a road. The effect softens sharp edges. Models can undo part of that softening, but not all. Choosing the observing wavelength is a compromise short enough to cut through some blur, long enough to pass cleanly through the atmosphere and remain bright enough to detect. Brightness matters, too. Sagittarius A times lives on a sparse diet. The flow of gas and dust into the center is thin, and much of what drifts inward is heated and swirled into a state that does not radiate efficiently. The glow is modest. Fainter emission demands longer integration and cleaner calibration, but longer integration invites smearing from the fast changes already at play. The analysis works at the edge between enough light to measure and too much variability to hold still. A world-sized instrument adds its own quiet complications. Each station must have clear skies at the right time, stable electronics, and clocks that do not drift. If a storm closes one sight, the imaginary mirror loses a piece. If humidity rises at another, atmospheric noise grows. Observing campaigns are scheduled for brief windows when the target is high at many locations at once. Even then, the weather must cooperate across continents and oceans. After the observing comes the careful work of putting the signals together. The data are too large to stream. They travel on drives to special centers where they are aligned by the timing of their clocks. Different teams try different ways of reconstructing an image, sometimes not knowing what the others are producing. Agreement among methods provides confidence. Disagreement sends people back to check assumptions about the atmosphere, the scattering along the line of sight, or the stability of the instruments. These practical issues matter because they shape what can be trusted in the final picture. A crisp edge is not expected. A ring of the right scale is. A brighter arc on one side is. Small asymmetries that survive many reconstructions and many choices about calibration begin to feel real. Features that appear only under one set of assumptions are set aside. It helps to remember that harder does not mean worse. The quickness of Sagittarius A times is a gift. Rapid changes allow tests that would take weeks or months around a heavier black hole. A short flare can be watched from rise to fade within a night. A hotspot may circle a few times before it dissolves. With more stations and multiple wavelengths, those brief events can be compared against the timing that gravity sets at 4 million solar masses, tying behavior to mass in a direct way. In a quiet way, the difficulties also guard against overconfidence. Variability forces humility. Scattering demands care. Weather insists on patience. What remains after these filters is a signal that has survived many chances to fail. That is why the ring of Sagittarius A times carries weight despite its softness. It is not a single snapshot caught on a lucky night. It is a consensus built from many small pieces that point again and again to the same outline. The contrast with M87 times offers a sense of scale and context. One shows us gravity working in slow motion on a colossal stage. The other shows the same rules playing out quickly in a modest arena nearby. Together they make the picture steadier. The same physics holds in both places, across a thousand-fold change in mass and timescale. For listeners, the comfort is simple. The universe behaves with a consistency that does not depend on our perspective. Whether the clock runs fast or slow, the pattern is the same. Gravity provides the shape of the stage around Sagittarius A*. It bends paths, sets the clock, and holds the center in place. Close in, though, another presence shares the work. Magnetic fields. They do not shine on their own. They are lines of influence drawn through hot, thin plasma-charged particles that carry the fields with them as they move. Where gravity is steady, magnetism is lively. It braids, tightens, and sometimes snaps. A quiet way to sense those invisible lines is through polarization. When electrons spiral around magnetic fields, the light they emit prefers a direction. Measure that preference, and the field's pattern appears as if traced by a soft pencil, ordered close to the black hole, more tangled farther out. Around Sagittarius A*, polarization maps suggest a structure with some coherence near the ring, a sign that the fields there are strong enough to guide the flow instead of merely riding along with it. Guidance matters because the plasma by the horizon is reluctant to cool. It is thin, hot, and swift. Gravity draws it inward, but magnetic stress can hold it up, redirect it, or encourage it to leave. In places where the field is wound tight, the pressure can dome the gas, lifting part of the flow into a weak outflow instead of allowing everything to sink inward. In calmer patches, the field lines act as rails, letting particles slide toward the center without much resistance. The result is not a steady river, but a shifting network of streams and eddies. Sometimes the lines are pulled so taut that they reconnect a change in topology that releases stored energy quickly. On the Sun, reconnection makes solar flares. Near a black hole, the process is harsher in temperature, but similar in spirit. A small region brightens, heats, and fades. Observers see this as a brief increase in infrared or X-ray light. The timing often fits the scale set by the black hole's mass. Minutes to an hour, a quick weather change compared with the slow seasons of stars. In some galaxies, Magnetic order near the center goes a step further and launches narrow jets beams of plasma shot out at high speed along the field's axis. The Milky Way's heart shows no long, brilliant jet. That absence fits its quiet diet. Still, hints of gentle outflows appear in radio and infrared, material choosing an easier uphill path along field lines, rather than committing to the inward fall. In a crowded core with little fuel, this is enough to keep the glow modest. Magnetic fields also help explain a pattern that might otherwise feel contradictory. The center is faint on average, yet capable of sudden flickers. A tidy field can suppress inflow, slowing the meal to a trickle. Stress builds. A small rearrangement, one knot loosening, one loop breaking, can liberate energy in a narrow patch. For a short time the patch is brighter, then the field settles and the calm returns. Nothing is lost from the larger balance. The average remains low. Close to the horizon, everything is compounded by relativity. Space-time drags a little in the direction the black hole spins. Field lines are not just twisted by the motion of the gas, they are dragged by the geometry itself. A hotspot circling near the edge may appear brighter when it comes toward us and dimmer when it recedes, a soft echo of the ring's asymmetry. Polarization turns with it, offering clues to the layout of the field in 3 dimensions. Farther from the center, the order weakens into turbulence. The plasma becomes less sure of its path. Heat can be carried outward by motions that look like weather more than traffic. Some of that energy leaves the system as a breeze that never becomes a jet. Some cycles back inward after cooling. Over long periods, the exchange keeps the region near Sagittarius A times from building the dense, brilliant disk seen in more active nuclei. The fields, by resisting an easy collapse, help maintain the underfed state. The picture that emerges is not a single mechanism, but a conversation. Gravity speaks with curves and clocks. Magnetism answers with threads and knots. The plasma between them negotiates how much falls and how much leaves. Even brief flares do not break the truce. They are moments when stored tension is paid out and the system returns to its low, steady hum. It is natural to look for a simple label. Some call this kind of flow inefficient, because it does not radiate much for the matter it processes. The word is accurate in one sense and misleading in another. The environment is efficient at staying quiet. Heat leaks away into motion rather than light. Fields carry energy without a blaze. For a galaxy that hosts life far from the center, this modesty is a gift. A noisier heart would leave a different imprint on its surroundings. All of this is learned from patient signals. Small changes in brightness, preferred directions in the light, subtle shifts that repeat. No single measurement is decisive. Together they paint a scene in which invisible lines keep company with curved space. And the center of the Milky Way remains calm, not by accident, but by balance. Most nights, the Milky Way's center is a low murmur, steady, subdued, almost shy. Then, with little warning, a brief brightness rises from near the edge of Sagittarius A*. It strengthens for a while, wavers, and fades. The heart goes quiet again, as if nothing happened. These are the flares, short-lived pulses of light in infrared and X-rays, bright enough to stand out against the usual hush, brief enough to feel like weather. They do not keep a schedule. Observers watch for hours or days before one appears. When it does, telescopes across the spectrum turn toward the center. Radio dishes listen for changes. Infrared cameras measure the rise and fall. X-ray satellites time the pulse from orbit. What emerges from all those ears and eyes is a pattern without a pattern. Flares vary in strength, some gentle and quick, others sharper and brighter, most settled within a couple of hours. The likely causes are simple in spirit and lively in practice. Near the horizon, thin, hot plasma slides along magnetic fields that twist and knot as the flow shifts. When a tangle tightens too far, field lines can reconnect, snapping into a new shape and releasing stored energy as heat and fast particles. That sudden push brightens a small region, which then cools and dims. Another source is infall. A slightly denser clump of gas wanders inward, heats as it approaches the black hole, glows for a short while, and disappears below the line where light cannot return. Both processes can happen, and neither needs to be large to be seen from our distance. In the calm of ordinary time, the flow around Sagittarius A times is underfed, diffuse, magnetized, and reluctant to radiate. Flares are the exceptions that prove the rule. They do not signal a change of diet. They are releases of tension inside a system that, on average, prefers quiet. If you imagine the region as a net of stretched threads and drifting sparks, a flare is a moment when one thread slips and a small patch flashes before the net settles again. There is a rhythm to many of these events. The rise is often swift. Brightness climbs in minutes. The fade is slower, as heat leaks away into motion and radiation. Timescales tend to match the clock set by a 4 million solar mass black hole. Close to the horizon, a small orbit can be completed in tens of minutes. Some flares seem to wax and wane with a hint of that orbital pace, as if a compact hotspot were briefly circling the edge, brighter when it moves toward us, dimmer when it moves away, then dissolving into the flow. Because the events are brief, coordination matters. Teams plan campaigns where ground-based telescopes and space observatories all watch together. The quiet stretches are part of the work. Patience builds a baseline. When a flare begins, measurements tighten. Spectra are taken more quickly. Polarimetry tracks the preferred direction of light. Radio arrays note whether the longer wavelengths respond and on what delay. These threads, woven later, reveal whether a flare was driven mostly by magnetic reconnection or by a pocket of gas falling inward. The differences are subtle but readable. Reconnection tends to energize electrons efficiently, producing sharply polarized light in the infrared and a quick X-ray spike that ends cleanly. A compact infalling clump may show a softer onset, with the infrared brightening first and radio emission following later, as particles cool and spread outward. In both cases, the flare's footprint is small, nowhere near the scale of the entire ring. The larger structure barely notices. It breathes and keeps its shape. Listeners sometimes ask whether flares are warning signs that the black hole is about to wake into something louder. The answer lives in the statistics. Over years, the overall rate of flares wanders within a modest range. Some seasons feel busier, others pass almost without a pulse. That drift likely reflects changes in the small supply of gas near the center and in how the magnetic field stores stress, not a transformation of character. A truly new era would require much more fuel, an incoming cloud dense enough to form a shining disk, or the distant future merger of galaxies funneling matter inward. Until then, the heart of our galaxy will remain quiet, with brief sparkles in the dark. Even so, each flare is useful. It serves as a flashbulb lighting up the near-horizon geometry for a moment. The timing can test how fast space-time flows at the edge. Polarization that rotates during a flare can trace the orientation of the magnetic field across an orbit. If a hotspot completes a partial turn before fading, its period hints at how close to the horizon it formed. Each small event is another measurement of the same object, taken in a different mood. Flares also teach restraint. They invite the imagination to leap. A sudden brightening feels like a story asking for drama, but the quiet average is the deeper truth. Most of the time, very little crosses the horizon. Most of the time, magnetic fields hold more than they release. The region is active by the standards of a laboratory and peaceful by the standards of a quasar. What breaks the calm is not a roar, but a spark. If you are listening near sleep, you might let the image soften into something simple. A deep well sits at the center of the Milky Way. Around it, thin fireflies of plasma circle on bent paths. Now and then, two threads meet, part, and a small light swells and ebbs. Then the dark returns, gentle and complete. The galaxy's heart keeps its calm. The flare becomes a memory in the data and a small step forward in our understanding. There will be more. The instruments watching are becoming more sensitive. More stations are joining the planet-sized camera that outlines the ring. Polarimetry is growing sharper. When the next bright flare comes, it will be read in more detail its shape, its timing, its favored direction. The event will pass in less than an hour, but the impressions it leaves will stay folded into the larger picture of a black hole that lives quietly, punctuated by brief, instructive light. Around many black holes, the sign of appetite is obvious. A bright, hot accretion disk, gas and dust, packed into a thin, shining ring that radiates fiercely as it spirals inward. At the Milky Way's center, that blaze is absent. The light is faint, the structure looks patchy, and the meal seems to arrive as a trickle rather than a stream. It is natural to ask whether something is missing. What we are seeing is not an absence so much as a different kind of flow. The gas near Sagittarius A times is thin and hot. Particles move quickly. They collide, but not often enough to share heat efficiently. Energy is carried around rather than radiated away as light. Much of the material that begins to fall inward stalls, warms, and then drifts outward again in a breeze. Astronomers sometimes call this a radiatively inefficient flow. It is an awkward name for a simple idea. The system is efficient at staying dim. The environment feeds that quiet. The central parsec does not supply a steady river of gas. Stars blow winds. Small clouds wander by. Fragments of material get stirred by the gravity of the crowd. But the supply is uneven and sparse. Without constant push of fresh matter, no brilliant, razor-thin disk forms. Instead, there is a puffy, magnetized flow that brightens modestly and fades again. Even in this gentle state, the edge can flicker. Small clumps of gas or knots in the magnetic field reconnect, and the region near the black hole shines briefly in infrared or X-rays. These flares rise and fall on the timescales set by a 4 million solar mass object, minutes to an hour, rarely longer. They are not signs of a feast, more like sparks from a hearth that never becomes a bonfire. Every so often, the center receives a visitor that seems big enough to change the pattern. One example was a dusty object tagged G2, tracked as it approached the black hole years ago. Some expected a dramatic brightening when G2 reached its closest point. Instead, the event passed quietly. The object stretched and blurred, and much of it survived, suggesting that it may have been a star wrapped in dust rather than a free cloud. The calm outcome fits the broader picture. The central flow prefers to resist sudden meals, redirecting or thinning them before they can radiate strongly. Measurements at millimeter wavelengths support this view. The ring we see is not a tidy, flat disk like those in textbook drawings. It looks uneven, with brightness that shifts and a thickness that points to a hot, puffed-up structure. Polarization hints at magnetic fields that both restrain and guide the plasma, helping to hold back efficient inflow and encouraging gentle outflows that carry heat and angular momentum away. There are also echoes of a different past. Far above and below the galaxy's plane lie large, faint bubbles seen in high-energy light. They hint that the center may have been louder at times, more active, more forceful. If Sagittarius A times once fed more vigorously, the present quiet could be a long pause between busier eras. In that sense, the missing disk is not missing at all. It is simply underfed right now, shaped by fields that favor balance over blaze. Thinking in simple images can help. Imagine trying to build a fire with scattered twigs. There is warmth, but no sustained flame. The air moves. The twigs shift. Now and then a bright spark rises and fades. Replace the twigs with a steady pile of dry wood, and the story changes. The center of our galaxy has twigs. It lacks the pile. Quiet feeding has consequences beyond appearance. A dimmer center is gentler on its surroundings. Less radiation leaks across the inner galaxy. Subtle outflows puff rather than blast, stirring the nearby gas without sweeping it clear. Stars can orbit closely without sitting inside the glare of a quasar-bright core. For a galaxy with planets far from the center, modesty at the heart is a kind neighbor. The calm does not mean nothing can change. A denser cloud could still drift inward. A cluster of stars could scatter and spill material close to the horizon. Over the longest times, even galaxies meet, and their cores awaken. But none of that has to be imagined to understand the present. The present is shaped by a light touch. Not enough fuel to build a thin, brilliant disk. Magnetic fields that keep the plasma from settling into one, and a geometry that trades heat for motion. The faint ring we have seen is therefore not a disappointment. It is a signature, the look of a black hole living on a diet that keeps it subdued. The absence of a blazing disk tells us as much about the conditions near Sagittarius A times as a bright one would. It says the neighborhood is tidy, the supply is uneven, and the fields close to the horizon are strong enough to slow what gravity would otherwise speed. Hold that picture in a relaxed way. A central glow that breathes rather than burns. A flow that circulates more than it crashes. Brief flashes that testify to stored tension released and then resolved. Nothing is missing. The story is simply quieter than the ones told by more ravenous hearts. Not every darkness in space is the same. The phrase black hole sounds singular, yet there are families and temperaments. All share one defining trait, a boundary where escape becomes impossible. Cross that event horizon and no signal returns. Outside that line, the details decide the mood, how much fuel arrives, how tangled the magnetic fields become, how many stars keep company nearby. Those details set whether a black hole blazes or keeps a dim, patient glow. For listeners settling down, think of categories as voices in a quiet chorus. Small voices carry quick rhythms. Large voices move slowly, like distant surf. At the heart of the Milky Way, Sagittarius A star is one of the large voices. It weighs about 4 million suns, and for now, speaks softly. Understanding how it fits among the other kinds will make its quiet feel less mysterious and more like a natural choice. Stellar mass black holes are the small end of the family. They form when very massive stars exhaust their fuel, lose pressure, and allow gravity to win. The core collapses. The outer layers may explode as a supernova, while the center continues inward, leaving a remnant only a few dozen times the mass of the Sun. We notice these small holes most easily when they feed from a companion star, building a bright disk that glows in X-rays. In the last decade, we have also heard them. Pairs of stellar black holes have crashed together and rung space-time like a bell, their waves caught by laser detectors. Their influence is local. Close by, they shape orbits and heat gas. A little farther out, they behave like any mass of the same size. Quiet, unless something wanders near enough to be torn apart by tidal forces. Between the small and the vast lies an elusive middle, the intermediate mass black holes. Evidence for them is suggestive rather than firm. Subtle extra motions in dense star clusters hint at a compact weight. Strange flares in some galaxies look like stars torn by something heavier than the stellar kind. A few gravitational wave events include partners weighing hundreds or thousands of suns. How might they form? One path could be repeated mergers of small black holes inside crowded clusters, building mass step by step. Another path could be the collapse of unusually dense clumps of gas before normal stars can assemble. If these mid-size objects are common, they may serve as seeds for the giants at galactic centers. If they are rare, the biggest holes must have grown quickly by other means. Either way, the middle helps explain how extremes are bridged across time. The search continues patiently. Supermassive black holes sit at galactic centers, weighing millions to billions of suns. Sagittarius A star belongs here on the light side, while others, like the one in M87, outweigh it by thousands. These giants do not appear in a single moment. They grow. Some growth is steady, fed by gas and dust streaming inward over long spans. Some arrives suddenly, when galaxies interact, stirring their cores and sending matter down the gravitational well. Central black holes can also merge, folding mass and spin together after their host galaxies collide and settle. A few candidates are larger still, ultra-massive giants deep in galaxy clusters, where supply and time have worked together for eons. Near such horizons, orbits crawl. What takes minutes around Sagittarius A star may take days or weeks there. The same rules apply, only the clock is stretched and the stage is larger. Growth writes their long biographies. Because nature is inventive, astronomers also test careful alternatives to the usual picture. A boson star made of hypothetical particles could be very compact, bending light strongly without a true horizon. A gravastar replaces the interior with exotic energy inside a thin shell. String theory imagines fuzzballs, where the interior is a tangle with no empty region at all. Some dream of wormholes, tunnels that join distant places. How would we tell the difference? If there is any kind of surface, falling matter should strike it and radiate, leaving a repeating afterglow. If there is no horizon, gravitational waves from inspiraling companions might carry tiny echoes. The exact size and stability of the dark shadow within the radio ring also matters. Different interiors bend light differently. Polarization patterns near the edge, mapped carefully over time, add another line of evidence. So far, every thread favors a real horizon for Sagittarius. A compact ball of dark matter at the center is far less likely. Without ways to shed energy and self-interact strongly, dark matter prefers broad halos over tight knots. A very dense cluster of ordinary remnants would heat and scatter itself, or collapse into a black hole anyway. Gravity by itself is simple about distance. Replace the Sun with a black hole of equal mass, and Earth would keep the same path. The drama happens only very near the edge. That is why galaxies are not swallowed by their hearts. Most stars live in peace. At the Milky Way's core, little fuel arrives. The plasma is thin and hot, and magnetic fields hold more than they release. The average glow is dim. Brief flares still appear, small sparks when a knot of field reconnects or a clump falls inward. Then the calm returns and the slow breathing continues steadily. Hold the catalog gently and the categories settle into one picture. There are black holes born from dying stars, possible bridges in the middle, and giants that anchor galaxies. A few speculative shapes linger at the edges of theory, reminders that humility is wise. For our galaxy, the simplest reading remains strongest. The motions of nearby stars, the measured size of the radio ring, and the lack of any surface glow All point to a supermassive black hole living quietly at present. Future measurements will keep polishing the portrait. Polarization maps will trace the magnetic pattern with more precision. Faster campaigns may catch brief hotspots circling the edge. One day, space-based detectors may hear a small object spiraling inward and test the geometry directly. Until then, let the thought be restful. The Milky Way's heart is dark, steady, and familiar, choosing calm while it holds the center close. Did the Milky Way's heart shape the galaxy? The clearest clue is painted above and below the disk. Two vast lobes glowing in high-energy light, called the Fermi bubbles. They rise like twin lantern flames from the center, stretching thousands of light years into the halo. Their symmetry is striking. Their rims are sharp. They are too deliberate to be chance. Something in the core inhaled fuel, then exhaled energy that left a lasting signature. What could have powered that breath? One scenario is a short active phase of Sagittarius A*, our 4 million solar mass black hole. For a while, gas flowed inward more freely than today. Friction and magnetic stress heated the plasma. Part of the energy vented upward and downward as a wind or compact jets, inflating the bubbles. Another possibility is a nuclear starburst, where massive stars lived fast and their winds and supernovae combined into a collective outflow. These stories are not rivals so much as accents of the same language. The center receives material. The center answers by returning energy to its surroundings. In both cases, the reply prefers the low-density path out of the disk, which naturally draws two lobes above and below the plane. The sharp edges suggest an impulsive event millions of years, not a constant drizzle after which the structures coasted, cooling slowly while keeping their shape. Multi-wavelength views strengthen that picture. Gamma rays fill the bubbles. Soft X-rays frost their borders. Radio filaments trace magnetic scaffolding. Even microwave maps show a matching glow. Put together, they read like a travel diary of energy moving outward from the core, compressing and heating gas, guiding charged particles along fields, and then fading. The scale is breathtaking. Each bubble spans roughly 10 kiloparsecs, about 30,000 light-years from the midplane to its crown. When did the exhale occur? Estimates place it in the recent cosmic past, perhaps a few million years ago. That is yesterday on galactic calendars. Since then, the Milky Way has rotated little. The central bar kept shepherding gas inward. Stars near the core have traced arcs around the dark mass. The bubbles, too big to disperse quickly, remain as slow memories cooling and persisting long enough to be our clearest evidence of an earlier, louder heart. What did they change? Close to the center, an outflow can heat or sweep gas, pausing star formation right next to the core. It can carry metals, the heavier elements forged by earlier stars, into the inner halo, where some mix and later fall back, thickening the chemistry of new generations. It can nudge magnetic fields and spread cosmic rays. On these scales, the heart's breath matters. It rearranges a neighborhood's timing without erasing the city it serves. What didn't it change? Most of the Milky Way's stars live far from the bubble's path. In the disk, spiral arms grow from its mass and rotation. The bar torques gas inward by its own dynamics. At the sun's distance, the black hole's pull is a whisper, and the bubbles are distant weather. They influence the inner regions. They do not redraw the outer map. The architect of the disk remains the disk. The bubbles also teach restraint. They show the heart is not locked in one mood. Today, Sagittarius A times lives on a sparse diet. The inflow is thin, magnetized, and inefficient. Brief flares sparkle and fade within an hour, but no steady beacon blazes. The bubbles record that another mode is possible when fuel arrives in quantity. The galaxy seems to balance modest inflows with occasional, effective outflows that keep the central regions from clogging. If you want a picture you can fall asleep holding, imagine breath. The bar and spiral arms draw gas inward. Inhale. Now and then the center exhales. Energy rides up and down out of the plane, carving two round lanterns in the halo. The inhale returns. Nothing essential has been destroyed. The system has simply kept itself clear enough to keep forming stars, clear enough to keep turning. The bubbles are that memory, drawn large and left to fade slowly. Could the heart speak again? Yes. Given the right delivery, a dense cloud might wander inward. A cluster could scatter, sending a few unlucky stars close enough to be stripped. In the very long term, the future merger with Andromeda will flood the center with fuel, rebuild the bar, and almost certainly awaken a brighter phase. None of this is urgent. On human timescales, the heart will remain mostly quiet, punctuated by brief, instructive sparks. So, did the heart shape the galaxy? It shaped its neighborhood decisively and whispered to the halo in a voice large enough to draw two scars. It likely slowed star birth near the core for a while, stirred metal into wider reaches, and tuned the rhythm by which gas drifts in and is sent back. But the grand architecture, the arms, the broad disk, the quiet country where we orbit, was drawn by mass and motion over long, patient turns. For tonight, that distinction can rest easily. We are far from the center, under ordinary stars. The faint afterglow of the bubbles reminds us the galaxy breathes, that its heart can speak without shouting, and that balance, not drama, has guided most of its life. Let that be enough. A calm core that once exhaled grandly, a disk that carried on, and a sky where both stories coexist while the Milky Way turns in unhurried sleep. There is a line around Sagittarius A times that isn't a wall and isn't a surface, yet it divides the possible from the impossible. Cross it, and nothing returns. Stay outside it, and light still finds paths to us. Physicists call that boundary the event horizon, and the simple number that sets its size is the Schwarzschild radius. For a non-spinning black hole of mass m, the radius is r, s equals 2 gm divided by c squared. Our galaxy's heart is roughly 4 million suns in mass, giving a Schwarzschild radius of about 12 million kilometers, or a diameter near 24 million. You could tuck the whole horizon inside Mercury's orbit. Light would take around 80 seconds to cross the diameter, barely a minute and a half, by a human clock. 3 related features help orient us. The horizon is the true point of no return. Slightly outside lies the photon sphere, where light can circle on unstable loops at roughly 1.5 Schwarzschild radii. Farther out appears the shadow, an enlarged silhouette, about 2.6 radii in size, etched into the surrounding glow by bent and swallowed rays. The Event Horizon Telescope resolves that shadow, not the horizon itself. On our sky, the shadow spans only tens of micro-arcseconds, comparable to a donut on the moon seen from Earth. No single dish could ever manage it, so astronomers linked radio observatories across the planet to act as one. For Sagittarius A*, another challenge appears. The ring's pattern evolves in minutes, so the data must be averaged carefully to reveal a stable outline. The horizon is not a thing you could touch. If you hovered just outside it, somehow canceling gravity's pull, no local alarm would sound. What changes is the map of possible paths. From far away, signals sent upward from near the horizon stretch to red and fade, so an infalling object appears to slow forever. For the object itself, time remains ordinary. The crossing happens and the journey continues inward. Mass softens some extremes. At a supermassive horizon, the tidal pull across a human body would be mild. Only deeper inside would stretching become severe. Yet the clock near the edge still runs quickly enough to notice change. A compact hotspot skimming the innermost stable orbit might circle in tens of minutes, brightening when it moves toward us and dimming as it swings away. Real black holes spin, dragging space-time around like a slow whirlpool. Spin pulls the inner orbits inward on one side, pushes them outward on the other, and can make the shadow look slightly squeezed depending on our view. For Sagittarius A times the observed ring is close to circular, which could mean a moderate spin, a viewing angle that hides distortions, or simply that turbulence blurs the subtleties. Between horizon and galaxy lies a restless skin of plasma threaded by magnetic fields. Electrons spiral along those fields at near light speeds and emit synchrotron radiation, the orange glow we reconstruct. In our galaxy, the flow is puffy and underfed. Much of the gas that drifts inward warms, stalls, and drifts back out. The result is a ring that breathes rather than blazes, with brief, unpredictable sparks. Because the shadow's size scales directly with mass, its angular width gives a clean cross-check. Combine the measured ring with the black hole's distance, and you recover the same 4 million sun mass that the nearby S-stars demanded through their orbits. Two independent methods, one geometric, one dynamical, meeting at one answer, is the quiet kind of certainty science trusts most. The image we share is an average, not a single frozen instant. Within it, theory predicts a razor-thin photon ring light that orbits several times before escaping, but present arrays blur that filament into the general glow. With more stations, faster cadence, and perhaps radio dishes in space, we may separate that thread and even make short movies of the ring's slow breathing. If you want a simple picture to keep near sleep, think of boundaries and echoes. The boundary is the horizon, a one-way door set by mass. The echo is the shadow, an outline traced by light that tried to pass and was bent away. Between them, magnetic weather flickers. Beyond them, the Milky Way turns. Numbers fix the scale. Calm holds meaning. The instruments that showed us a soft ring around the Milky Way's heart are not standing still. They are being sharpened, multiplied, and taught to listen in new ways. The next few years will not just add detail, they will change how we watch Sagittarius A*, less like a single photograph and more like a slow, breathing film. Begin with the planet-sized camera itself. The Event Horizon Telescope is becoming the next generation EHT by adding stations, widening bandwidth, and observing at multiple millimeter wavelengths at once. More stations fill the empty spaces in Earth's virtual mirror, which turns a fuzzy outline into a steadier ring. Wider bandwidth means more signal and cleaner reconstructions. Observing at two nearby wavelengths, think 1.3 millimeters and 0.87 millimeters, helps peel apart scattering by interstellar dust from true structure near the horizon. At the shorter wavelength, the view sharpens. At the longer one, we retain sensitivity when the weather turns thin. Faster cadence is part of this upgrade. Sagittarius A times changes in minutes, not days. So the array is being trained to take quicker snapshots and to stitch them into short movies. That pace lets us watch a hotspot circle the inner edge, see brightness slide around the ring, and separate brief flares from the steady glow. In those sequences, subtle fingerprints of gravity appear, beaming on the side, moving toward us, delays on the side receding, and the hint of frame dragging if the black hole's spin tugs space-time strongly enough. Another new eye is polarization. Light carries a preferred direction when it has danced with magnetic fields. The EHT already made first polarized maps. The The next maps will be sharper and faster, tracing how the field lines twist, reconnect, and relax during flares. If the field organizes itself into a coherent spiral, the pattern may reveal the tilt of the black hole's axis. If it breaks into tangled patches, we learn that turbulence and reconnection dominate the inner flow. Above the atmosphere, IXPE, the Imaging X-ray Polarimetry Explorer, adds a different kind of compass. X-rays come from the hottest electrons closest to the brink. Their polarization rotates and strengthens depending on geometry, magnetic order, and spin. During a bright flare, IXPE can watch that orientation swing in real time. A smooth rotation hints at an orbiting hotspot near the innermost stable path. A sudden flip favors magnetic reconnection. Over many events, the statistics tighten into a portrait. How often flares are magnetic versus infall, how near the edge they ignite, and whether a preferred axis guides them. Closer to the ground, yet above the blurring air, gravity at the Very Large Telescope Interferometer continues to pin stars and flare hotspots to the sky with exquisite precision. Its upgrades, often called gravity, plus push deeper into the crowd around the black hole. With that precision, we can watch the gravitational redshift of a star near pericenter, or the tiny precession of its orbit from Einstein's curvature. When a compact knot flares in the infrared, gravity can sometimes trace its tiny loop, a silent clock hand sweeping within a few Schwarzschild radii. New mirrors are joining the chorus. The extremely large telescope in Chile, with a segmented primary 40 meters across, will bring adaptive optics strong enough to cut through the dust and resolve fainter stars still closer to the center. The giant Magellan telescope and the 30-meter telescope add their own power. These eyes will weigh the dark heart indirectly by tracking ever tighter orbits and will probe how stars form and survive in such an intense tidal field. At radio wavelengths, sensitivity is rising. ALMA continues to be the backbone of the EHT, and its planned, wide-band, low-noise receivers will collect steadier baselines in marginal weather. The coming NGVLA next-generation Very Large Array will map cooler gas and the faint outflows that carry heat and momentum away from the center. Farther down the spectrum, the Square Kilometer Array will reveal the spiderweb of non-thermal filaments and the sea of low-energy cosmic rays that thread the central few hundred light-years, giving context to the black hole's gentler influence. Coordination is becoming a feature, not an afterthought. Networks of telescopes now run triggered campaigns. When an infrared spike begins, alarms wake radio dishes and X-ray satellites. When the radio brightens first, infrared eyes turn to look. Data pipelines are being tuned for near real-time reduction so that the array can decide during a flare which cadence and wavelength mix to use next. The result is not just more data, it is more connected data, where each photon knows the company it kept. On the horizon is an idea that turns the Earth-sized mirror into something larger. Space, VLBI at millimeter wavelengths. A modest dish in high orbit, and one day, perhaps, on the moon linked with ground stations, would extend the longest baselines, sharpening the ring and isolating the photon ring, the razor-thin set of paths from light that loops the black hole before escaping. With that extra reach, the difference between a circular ring and a slightly squeezed one could settle the spin more cleanly. With continuous coverage day and night, we could follow the ring without the gaps that sunrise and weather impose. Other instruments fill in the environment that feeds the heart. JWST maps the warm dust and complex molecules in the central molecular zone, showing where the next clouds may drift inward. High-energy observatories like Chandra and XMM Newton watch the faint X-ray glow that marks shocks, winds, and the quiet simmer of hot gas. Together, they explain why the accretion flow is underfed, and why most of the material that approaches ends up circling, heating, and drifting outward again. What all these new eyes promise is simple to say and deep to feel: time. Instead of one picture, we will have sequences. Instead of one flare, statistics. Instead of a single polarization map, a changing field. Time turns images into behavior, and behavior into understanding. It lets us test whether the ring's size truly stays fixed, as mass demands, whether hotspots truly orbit where theory predicts, whether the field near the edge is orderly or wild. If you need one idea to hold as you rest, make it this: our view is becoming closer, not by traveling there, but by learning to listen longer and more carefully. The instruments are the same sky watchers as before: mirrors, dishes, detectors, but arranged with more patience and in better company. They will not make the heart louder, they will make it clearer. And in that clarity, the silent monster at the center of the Milky Way will feel a little less distant, and a little more like a heartbeat we can learn to read. We've watched the Milky Way's heart by following light, radio murmurs, infrared embers, sudden X-ray pricks, but gravity speaks too. When heavy bodies move, they wrinkle space-time and send ripples outward. Those ripples pass through dust, gas, and glare as if they weren't there, carrying only the rhythm of motion. If we can listen to the center with this other sense, we'll hear not brightness, but orbits slowly turning into endings. Picture a compact traveler, a small black hole, or a neutron star caught by Sagittarius A*. It circles once, then again, losing a breath of energy each time. Over thousands to millions of loops, the path tightens. With every sweep, it shakes space-time, and a whisper runs outward. This is an EMRI, an extreme mass ratio in spiral. Tiny companion, enormous anchor, a story told in long patience rather than sudden drama. EMREs sing in the millihertz band, too low for ground observatories. Instruments like LIGO and Virgo are tuned to the quick chirps of stellar black holes, colliding frequencies hundreds of times higher, because their arms span only a few kilometers, and the Earth itself is noisy. To hear an EMRI, you need a detector larger than the noise of our planet, and calmer than its shifting ground. That ear will float in space. The Laser Interferometer Space Antenna, or LISA, will be 3 spacecraft forming a wide triangle, millions of kilometers on a side, joined by laser beams. As a gravitational wave passes, those separations stretch and shrink by less than an atom's width. LISA watches that tiny sway by timing light over vast distances. No atmosphere, no earthquakes, no trucks. Only the quiet expansion and contraction of the triangle's sides as gravity hums through it. If a compact object spirals toward Sagittarius A*, its note will linger months to years inside LISA's data. The pitch will drift upward slowly. The tempo will quicken by imperceptible steps, loop after loop. Laid over that rise are fingerprints of the space-time itself, precession that twists the ellipse, and the gentle tug of spin as the black hole drags space around like a slow whirlpool. The melody is simple. The phrasing is full of information. What can be read from that song? Waves encode geometry. From the pattern alone, we can measure the mass and spin of the central black hole with precision that light often can't match. We can test whether the orbit's precession fits Einstein's prediction for a Kerr black hole, whose exterior is defined only by mass and spin. Over tens of thousands of cycles, even tiny mismatches grow large enough to notice. Agreement tightens trust. Disagreement, if it persists, points toward new physics. EMRIs also map the neighborhood before a small black hole begins its long fall. It must find the center nudged inward by chance encounters with stars, by the breakup of a binary skimming too close, or by friction if a thin gas disk is present. The rate of EMRIs tells us how many compact remnants live in the inner parsec and how strongly mass has segregated there. A true inspiral is precious. Even a near miss, a compact body on a tight eccentric path, would leave a steady line in Liza's band for years. The Milky Way may or may not offer an EMRI during Liza's watch. Patience is part of the plan. But the instrument won't listen to us alone. It will hear countless white dwarf binaries humming across our galaxy. It will catch inspirals into heavier black holes in other galaxies where the pitch sits cleanly in the millihertz sweet spot. Each detection becomes a case study in strong gravity, written not as a snapshot, but as a measured rhythm. Listening won't replace seeing. The two will complete each other. If Lisa hears a compact body sweeping close to Sagittarius A asterisk, the EHT next can stare at the ring while the rhythm slowly climbs. Gravity can watch for a faint, clock-like loop in the infrared. IXPE can track the swing of X-ray polarization if the passing body perturbs hot plasma near the brink. Light will show how the environment responds. Waves will trace the motion that drives the response. Together they turn a single event into a layered portrait. There is a softer ambition too. General relativity says that isolated spinning black holes are simple beneath their drama. Mass and spin determine everything. The sequence of multipole moments follows a strict pattern. Horizons absorb. They don't echo. EMRIs test that claim with exquisite patience. If the heart had a surface or a strange interior, the wave would carry faint afterbeats or slightly wrong precessions. Over many cycles, those small wrong notes would accumulate. If they never appear, we learn again that the simplest reading holds. If you want one image to rest with, imagine Lisa as a harp stretched across space. Its strings are laser beams. Gravity plucks them. Most of the time, the instrument hums with background notes from quiet binaries, like city lights in sound. Now and then, a slow melody starts the long approach of a small companion toward a dark center. The tone glides higher by the tiniest steps, circles tighten. And then, at the horizon, the music slips beyond hearing. No flash is needed. The end is written in the rhythm itself. Even silence is useful. If Lisa hears no EMRI from our center, that absence still narrows how crowded the inner parsec can be with compact remnants and how efficiently they drift inward. Either way, we will hold a clearer picture, a heart outlined by images, tempered by flares, and timed when the universe allows by gravity's own unblinking beat. Far ahead on the Milky Way's path, a quiet meeting is set. The Andromeda galaxy drifts toward us, and over billions of years the two spirals will fold into one. It won't be a crash in the way rocks collide. Space between stars is wide, and most will pass without touching. The true drama will be softer. Gravity rearranging orbits, rivers of gas changing course, and two dark hearts feeling for each other through the crowd. First, the approach. From our vantage, Andromeda brightens almost imperceptibly with each long turn of the galaxy. Tidal pulls grow stronger. The outer halos touch, and threads of dark matter and rare, hot gas begin to mingle. The first pass will stretch both disks, drawing out tidal arms, long, pale streamers of stars and dust that curl like ribbons. Some stars will be tossed to great distances. Some will fall inward. The bar at our center may strengthen, then twist. The central molecular zone will feel fresh pressure and new supply. The sky will change for any future watchers. Andromeda will grow from a hazy smudge into a wide sweep of light, then into a tangled double spiral laid across half the heavens. Over millions of years, The two patterns will overlap and blur. The scene will be slow and grand, a transformation you notice only by memory and by stories passed down, not by a single night. In the core, the meeting becomes intimate. Sagittarius A times and Andromeda's central black hole M 31 times will sink toward each other through dynamical friction, losing momentum to the swarming stars around them. Orbit by orbit, they spiral inward, throwing off energy in ripples of gravity that a future space observatory could hear. Before they merge, the inflow of gas into both centers will likely surge. For a time, our quiet heart may shine like a modest, active nucleus. The ring brightens, winds lift from the inner disk, and the halo answers with faint, distant glow. Star formation will flare in bursts, where streams of gas collide and compress. New clusters will light along shocked filaments, and supernovae will follow, adding their own brief punctuation. Some of those newborn stars will be born on orbits that carry them far from where they began. Others will settle near the reshaped center. The chemistry of the inner regions will thicken as elements forged in earlier generations are stirred and spread. Closer to home, the solar system, if it still exists, will feel these changes mostly as a shift of neighborhood. Direct impacts are unlikely. Encounters at vast distances are enough to tug at orbits gently. The sun may be nudged outward, inward, or simply elsewhere in the new galaxy's broader envelope. In many simulations, our star ends up farther from the final center, under darker skies. But the possibilities are many, and the timescales are long beyond measure. Whatever happens, it will happen slowly, with no single day when everything changes. When the two black holes finally meet, it will be quiet in light and loud in gravity. Their horizons will touch and combine, and the new center will ring for a moment in waves that carry news across space. The merged heart will be heavier and may spin differently, its axis set by the last turns of the inspiral. That spin will shape how future jets, if any, aim into the halo, and how the inner flow sorts itself when fresh gas finds the well again. After the stir and brightness, the system will relax. The spiral arms will fade into shells and streams. The bar may survive or be reborn. The disk will puff into a more rounded form. Astronomers call the likely outcome a giant elliptical or a smooth, lens-shaped remnant less ornate in structure, but tranquil. New stars will still form where gas remains, though more slowly. The central black hole, now the combined descendant of two, will spend long stretches as ours does now, underfed, steady, punctuated by brief, instructive flares. It is natural to wonder about danger. High-energy outbursts from the center could be stronger during the active phases, but distance is a patient shield. Even a brighter nucleus would soften with a long journey across the galaxy. Close to the core, worlds might feel more of that light. Far in the suburbs, where we likely will be, the change would be a glow on the horizon more than a storm overhead. In this future, time is the gentlest teacher. The merger is not a single event, but a sequence. Approach, first pass, recoil, second pass, and gradual union. Each stage writes a layer into the sky, streams of old stars arcing outward, knots of new stars kindled in compressed gas, a heart that wakes and rests. What looks like violence from afar is, in the frame of a star or a planet, a slow reweaving. If you want a calm picture to hold as you drift to sleep, imagine two slow tides meeting. The currents cross, swirl, and find a common flow. At the center, the deepest part of the sea grows a little deeper, and for a while waves run farther up the shore. Then the water settles into a new shape. The new galaxy turns quiet again, with a heavier heart and wide, settled skies. Our place in that future is uncertain in detail but safe in pace. It will be a change written in long patience. A story the universe tells in movements far too slow to startle. From a small world far from the center, it's fair to ask why the Milky Way's heart matters at all. A soft ring, brief flares, a patient breath. How does any of that touch a life under ordinary stars? The answer begins with time. Sagittarius A times is quiet in our era. In a universe where galactic cores can roar, ours is subdued. That quiet buys stability. Planets cool, atmospheres persist, oceans hold their chemistry, and life, wherever it appears, gets long chances to try, fail, and try again. Safety follows. Even when the center stirs, distance is a patient shield. Radiation from a modestly active nucleus softens over tens of thousands of light years. Close to the core, worlds might feel harsher weather. In the suburbs where we orbit, the change would look like a glow on the horizon more than a storm overhead. The history written into the Fermi bubbles hints at past exhalations, and yet here we are downstream and unscorched. Quiet at the heart gives space for calm at the edges. The heart also helps set the tempo of creation. Outflows from the center can puff, heat, or sweep nearby gas, slowing starbirth where it would crowd the core, then seeding the halo with heavy elements that later rain back. Over billions of years, that cycling enriches the disk with carbon, oxygen, and iron, the ingredients of stone, water, and blood. We are literally downstream of that patience. The atoms in our bones are loans from many generations of stars, nudged and mixed by the city's breathing. Practical gifts arrive from the way we look. To image a donut-sized ring at the distance of the moon, we learn to synchronize atomic clocks on mountaintops and deserts, to ship petabytes with care, to knit signals from many continents into one eye. Those same skills refine navigation, geodesy, and communications. Better clocks mean better GPS, cleaner correlations, and compression help. Everything from climate sensing to medical scans. The curiosity that stared at a black hole quietly upgraded the tools we use every day. The center anchors physics too. The orbits of the S stars and the measured ring size test gravity where space-time curves most strongly, while still letting light escape. Each agreement tightens our trust in the models that steer spacecraft and track the universe's expansion. Each tension, should one appear, would be a lantern held up to new ideas. Even silence instructs. If predicted echoes never arrive, if flares favor one mechanism over another, we adjust the map we carry into every other measurement we make. The project itself is a lesson in cooperation. A planet-sized eye is impossible for any one nation, but ordinary ones many share the same sky. Observatories at the South Pole, in Chile, in Hawaii, in Europe, and beyond, synchronized to a heartbeat no border could keep. That habit of attention, patient, distributed, generous, spills over into other global work. The image of the ring is also a picture of how curiosity behaves when we let it cross lines. Quietly, steadily, and with results none could build alone. It also gives context. Our calm neighborhood is not an accident. It's part of a structure with a bar, a bulge, and a dark anchor. Knowing that pattern makes the map in your head feel sturdier. You can point toward the center and imagine the crowded stars, the puffy, magnetized flow, the delicate ring that outlines the edge of the possible. Children can grow up with that picture as normal. Awe becomes familiar, and familiarity invites questions, the seed of every new measurement we will someday make. Finally, there is calm that comes from scale. The future merger with Andromeda sits billions of years away. The flares that decorate the core fade within an hour. The black hole's pull at our distance is a whisper. We are safe enough to be curious. That is not nothing. It is a condition worth noticing. The heart's quiet lets worlds like ours persist. Watching it teaches us to keep time, to coordinate, and to test ideas honestly. It gives our small place a patient frame and meaning without hurry. If anything, it asks us to listen together and let wonder turn into shared, careful knowledge for everyone. We have walked to the edge of light far enough to see a ring stitched from radio whispers, close enough to feel how space itself leans toward a center we cannot cross. We have watched stars wheel in tight ellipses, seen flares wake and fade, traced two pale lanterns blown into the halo, and listened for the slow music of gravity. All of it converges on a dark weight that keeps time for the Milky Way. And yet a question remains, simple enough to carry and large enough to last. What does it mean for a galaxy to have a heart you cannot see? Perhaps it means that absence can still have shape, that something defined by what cannot escape still writes the motions of everything around it. Perhaps it means that quiet, not spectacle, is what holds most stories together. The center has been many things, louder, softer, patient in between. Its breath has rearranged a neighborhood without unmaking the city. Even now, while we sleep under an ordinary sky, the ring brightens and dims by minutes we don't feel. Our instruments will keep learning to listen faster images, truer maps of magnetic lines, long songs from small companions spiraling in. Each will bring the edge into slightly clearer focus. None will tame it. A horizon is a boundary not only for light, but for knowing. That is not a failure. It is an invitation. So let the lingering question stay. Let it sit beside whatever tomorrow needs. When you think of the Milky Way, see the slow disk, the bright bulge, and at the center, a patient darkness that does not ask to be feared. It asks to be noticed. It asks us to pay attention together, to keep time with it, and to wonder what else in our own lives is shaped by quiet forces that rarely ask for credit. The galaxy turns. The heart holds. We listen.